I am Vishwanath Banerjee. I am a faculty member of Department of Civil Engineering, IIT Kharagpur. I will be second instructor for your this course matrix analysis of matrix structural analysis. So, we have module 3 today, and it is the first lecture for the module 3. So, here we will review the basic matrix algebra. Because the objective, one of the objective for this course is to do large scale structural analysis, which requires knowledge of solution of matrix vector equation. So, for that we need knowledge of structural for little bit knowledge of matrix analysis. All of you have this basic knowledge, but in this module we will basically review this some of these matrix analysis, and then we will move to the conventional structural analysis, where we will use the sum of these matrix algebra. So, in this course we will be covering mainly matrix and its in this module we will be covering mainly matrix and its properties, determinants, matrix inverse, solution of linear system of equation, rank and linear independence, and then finally we will consider the flexibility and stiffness matrices and its properties, which are very important for solving the large scale structures, that means where the degrees of freedoms are large. So, probably by this time you have learned the what is stiffness of a structural component, what is flexibility of a structural component, all those things you have learned. So, finally, it boils down to a matrix which is popularly known as stiffness matrix or flexibility matrix, and then by which we solve those structures. Some methods probably you have heard are force method or flexibility method or compatibility method, and stiffness method or the displacement based method. So, basically in a structure this kind of equation we will encounter, we will be giving details for this kind of equation. So, one of them is stiffness method, where the equation will be like this: k delta equals to f, where k is the stiffness matrix, delta is the unknown displacement vector may contain the rotation also, and then the known force vector. So, this is popularly known as stiffness method or direct stiffness method. And another method we will also discuss in latter part of this course is the force method, where we will use the flexibility matrix F and then the unknown force and with the known displacement. So, this is also known as the force method. So, to solve these equations finally we need some knowledge of how to solve this equation. For instance, probably you have already learned the Gaussian elimination, LU decomposition, or any other method like QR decomposition. So, we will just briefly review these things before we jump into these equations and how these equations are formed. So, to start with, we will just how matrix comes to us. Actually, our main objective is to solve some equation. So, for instance, this is a 3 simultaneous linear equation which can be represented in a matrix form, that is the matrix A and matrix A and unknown vector as x, and right hand side or the force vector is b. So, if you look carefully that the coefficient of these equations are arranged in a row and column wise, so that it forms a matrix. So, here it is there are 3 equations. So, this is a third order matrix A, and so it can be generalized. If you have n number of equations, it can be generalized as nth order matrix, but matrix can be rectangular also. So, if I write any matrix A in terms of its component A 1 1 to A 1 n and m, then A 2 1 and so on, and then m 1 to m n. So, this is a rectangular matrix of dimension m n, which means m rows and n columns, right. So, now we will be mostly dealing with the square matrix where m is equals to n. So, for instance, the matrix A we sometimes write in this form, the Aij. Okay. The matrix A sometimes we write in this form, that its component form, right, which means I runs from 1 to n and j runs from 1 to m or n. But we will be mostly dealing with the square matrix. So, do not bother about rectangular matrix here. So, this is a basic notation we will follow, and sometimes we will also write the row vector and column vector. For instance, if I write this vector x is a column vector. Column vector means if we have x, y, z, this I am writing as a column vector. If you look carefully, the dimension of this matrix is 3 cross 1. But if I want to write a row vector, right. So, for instance, here the row vector for this matrix is 2 2 1, right. This is a row vector. Now, if you look carefully, its dimension is 1 cross 3. So, this is just a preliminary definition, and then we will now determine some of the matrix properties or different types of matrix. For instance, the diagonal matrix. Diagonal matrix means it's all diagonal elements, all or some of the diagonal elements are non-zero, but off diagonal elements are 0. That means, if Aij equals to 0, if I not equals to j. So, if you look carefully, this is the third order matrix where first row, in a first row all of diagonal elements, that means these elements are 0, right. So, these elements are 0, all of diagonal elements are 0, right. So, similarly we define identity matrix where all diagonal elements are 1 and off diagonal elements are 0. So, if I write, for instance, identity matrix of order n, that means it is a nth order matrix whose diagonal elements are all 1. So, this is the basic definition of diagonal and identity matrix. Sometimes we also represent diagonals of a matrix. So, this has to be looked carefully. So, diagonals of A, here A is a 3 cross 3 matrix. So, diagonals of A are the diagonal elements of A, that is 2, 1 and 0, which we write sometimes diagonals of A like this, and this is a matrix, this is a vector which contains the all diagonal elements. So, now the transpose of a matrix. The transpose of a matrix means it's if you just flip the row and columns of the matrix. That means, here this is a 3 cross 3 matrix. You see these blue letters goes up and red letters go, red numbers goes down in a transpose. So, by definition we can say that A transpose I j is A j I. That means, the off diagonal elements are changed. So, inverse of a matrix, all of you have heard inverse of a matrix. So, inverse means there exists a matrix for which if you pre-multiply or post-multiply with the matrix to be inversed, if you pre-multiply or post-multiply, pre-multiply and post-multiply, it will be identity. So, this also you have learned in your first year course probably, and then one of the properties of the inverse is AB inverse is, that means the product of two matrix and then taking its inverse is B inverse A inverse. So, these properties can be validated for the 3 cross 3 matrix, or it can be proved also, but we will not go into details of this proof because we will just use it here. Now, another type of matrix will be very important for us is upper triangular matrix. That means the matrices which has only upper parts are non-zero and the lower part are 0. That means the diagonal elements are non-zero and the upper part of the of diagonal elements, these parts are non-zero. But carefully, if you look, the lower part of the matrix is 0. Similarly, we can define lower triangular matrix where the lower part of the upper part of the matrix is 0, upper off diagonal elements of the upper part are 0 and the off diagonal elements in the lower part is non-zero. Okay. So, then we will go for symmetric matrix. So, since we have defined transpose, we can now define symmetric matrix. If a matrix A transpose is A, then we say the matrix is symmetric matrix. That means the off diagonal elements are same. That means Aij, if Aj, if Aij is equal to Aj, then we see that matrix is symmetric matrix. Now, similarly, skew symmetric matrix. Q symmetric matrix is if A transpose A is equals to minus of A transpose, then we say this is a symmetric matrix. Now, as a consequence of this, if you write this equation carefully, then you will see that A plus A transpose is a 0 matrix. So, if you write this equation, if you take this A transpose this side, then A plus A transpose is 0, which finally results that all diagonal elements has to be 0, right. So, the skew symmetric matrix or sometimes also known as antisymmetric matrix is if Aij is minus of Aij when I not equals to j. That means the off diagonal elements of the matrices are negative, but they are same in magnitude, right, only sign flips. So, here for instance, this 1 2 element is just a negative of 2 1 element. Similarly, all other off diagonal elements. So, any matrix can also be represented, any matrix can be represented in terms of a skew symmetric part and a symmetric part of the matrix. This proof is also very similar, but we will not, as we discussed earlier, we will not discuss the proofs, mainly here we will use the results. So, this is a skew part of the matrix, skew part of the matrix or skew symmetric part, and this is the symmetric part. So, this form sometimes we will use, that a matrix can be decomposed into a skew symmetric matrix and symmetric matrix. Now, similarly, the we can define banded matrix. For instance, the banded matrix means where the all non-zero elements of the matrices are arranged or gathered towards its main diagonal element. For instance, look this matrix A, where the all non-zero elements are located near the diagonal element. If I draw a line here, so it's look like this. So you can see that this matrix clearly shows a band, which actually helps us in solving this matrix, that we will learn later part of this course. So sometimes we need to feed the bandwidth of the matrix so that our solver can be effectively utilized. For instance, if you want to calculate the band, so bandwidth, so here the S is the largest number of columns from the diagonal which will have non-zero element. For instance, if you look this matrix, this is the this is the S. Okay. So, this S, how I calculate this S? If you look carefully, all diagonal element, maximum number of non-zero elements are only 2. So, this is my the bandwidth of the, this is my S. So, my finally bandwidth will be 2 into 3 minus 1, that is 5. So, how I get the 5? The 5 I am getting in this way, that maximum I can have this from the diagonal I can have 2, and from this diagonal I can have 2 more non-zeros here. So, this is how we calculate the bandwidth of the matrix. So, another matrix sometimes is useful is tridiagonal element, tridiagonal matrix. This matrix is occurring in terms of when you do finite difference calculation, this type of matrix appears. So, sometimes it is also known as the finite difference operator. So, if you look carefully, this tridiagonal matrix, that means it has a bandwidth of, 3, because how I calculate 2s minus 1. So, s is 2. So, 2 into 3, 2 into 2 minus 1. So, why 2? Because S is here, S is my 2, but it should be remembered that this S may not be only in the first row, this is the maximum number. So, it can appear in any row, even though for this course this matrix, this is same, this has to be the same. So, here also if you see, this is the S is the 2. So, this bandwidth of this matrix becomes 3, right. So, this also has a specific advantage when we learn LU decomposition of a matrix to solve a matrix vector equation. This type of matrix properties helps us in decomposing the matrix, or sometimes known as factorizing the matrix. So, this property sometimes we will use. So, it is always better to know this properties. So, now I think all of you know matrix addition and matrix subtraction. So, matrix multiplication also you know, but I will just review once. This is a matrix A B multiplied with C. So, A B can be multiplied, A can be multiplied with B if M has A has M cross n rows and M rows and n columns, and if B has n rows and q columns, then only it can be multiplied, otherwise it cannot be multiplied, right. So, and this if I write in initial notation, it looks like this. So, where k we runs from the number of columns. Clear? Now, if we look these properties of matrix multiplication, sometimes it is very important, and also it is important to know these properties. These properties, the first property is it is distributive. What does this distributive means? That means, if I add first two matrices and then pre-multiply the matrices, another matrix A, then that will be equals to the post multiplying the matrix B with A and matrix C with A. This property is known as distributive property. In the same sense, if I write this property, so in a different way, for instance, if I want to write A plus B first and then C I want to post multiply, then this product will be matrix A, then matrix C plus so this is the distributive property. Then matrix, the second property is associativity. So this also, if I just pre-multiply matrix A with the product of matrix B and C, then that will be equals to the if I post multiply with A and then the product I post multiply with C. Similarly, this can be if I want to write AB, for instance, matrix A, then matrix B with matrix C. So this I can write in this way. This property is known as associativity. Right. Another property is non-commutative property. In general, matrix products are not commutative. What does this commutative means? This A, if you post multiply with post multiply B with A, that will not be equals to pre-multiplying B with A, which is actually the important property, that matrix properties are non-commutative, but there are certain exception. For instance, if the matrix B is an identity matrix, which is I, we have defined identity matrix, that means all diagonal elements are 1, then this will be satisfying the commutative property. That means, if I post multiply I with A and then if I pre-multiply I with A, those two matrices will be equal, but this is an exception. In general, this is valid. Now, there are some properties of matrix transpose also. For instance, the A plus B, if you want to transpose, which is equals to A transpose B transpose. If you multiply two matrices and then transpose it, then it will be B transpose plus A transpose. If you want to multiply a scalar with matrix A, then you can take out the if you multiply scalar with matrix A and then transpose it, that will be equivalent if you take out the scalar outside and then transpose the matrix and then multiply this scalar with this matrix A. So these properties are a very simple one, and we need to remember these properties. Now, another matrix probably we need is the orthogonal matrix. Orthogonal matrix can be defined as the matrix whose columns are orthonormal. Okay. So, we will discuss what is orthonormal and all those things. We will not discuss here, but it is important to know here for this course that an orthogonal matrix is that for which its transpose is actually its inverse. So, this is the property for the orthogonal matrix. Now, determinant is a scalar, is a nonlinear scalar function. So, remember one thing, this is a nonlinear scalar function. So, when we say determinant, we always say that determinant is something which is a scalar value. So, determinant can be represented as the ai1 ci1 plus ai2. That means the determinant of a matrix is a combination of rho I and the cofactors of rho I. So, we will see what is cofactor. The cofactor of a matrix is the determinant of the minors with proper sign. That means the cofactors are essentially determinants. So, if I can compute the minors of matrix A, which is Mij, and its sign if we take carefully, then we say this is the cofactor of ijth cofactor of matrix A. So, how these minors are formed? These minors are formed by deleting ith row and jth column of the matrix. So, we will see once. For instance, this is a matrix 3 by 3 matrix. We want to calculate the determinant. So, if I want to write this is the formula for which we have discussed just now. So, the cofactors of C11 is essentially the C11 is essentially the minus 1 plus 1 determinant M11. So, what is M11? The M11 is actually, so this will be plus 1, right. The M11 is the determinant of removing first row and first column. That means, if I remove this row, this column, then this is the case. So, it will be A22, A23, A32, A33, right. Similarly, for the others. So, this determinant is simple, A22 minus A33 and A22 into A233 minus A23 into A32. So, similarly, for the other case, the deleting the second row and the second column and the first row and the third column. So, we will get the determinant of the matrix. Now, so, determinant's property. So, as I have said, determinant is a nonlinear function. So, its summation won't be just det A plus det B and then product of two matrices, and taking its determinant is the taking individually its determinant. So, det of AB is det of A into det of B. So, if you want to pre-multiply a scalar, that is det of k into A, so it will be k to the power n det of A. So, this n is the order of matrix. Another property is the cofactor property of the determinant, that inverse of the calculation of the inverse. So, an inverse is essentially 1 by det of A of cofactor. So, this A cof is the adjoint matrix. So, whose elements are cofactors of A. So, A cofactor is generally known as the adjoint of A. Adjoint of A, and then C ij is a cofactor and then its transpose. So, this is we will see in a detailed manner in the next lecture. So, this cofactor matrix was also known as the adjoint matrix, which is the transpose of the cofactors of a matrix A. So, we will see this in the next lecture in detailed manner, and we will compute the inverse of a matrix. So, thank you.